So we're going to dive right into section 1.1 in this video. And the section 1.1 is really about modeling using differential equations. And so it's going to establish some kind of systems and norms that we use for modeling. And the first thing we need to do is understand about mathematical modeling. What do we do and why do we do it? And so there's a real number one reason why we use mathematical modeling, and it's because it does useful things. Now, it may seem strange and trite to kind of say it that way, but remember, we don't do things in mathematics unless they're useful, or sometimes we do them just because they're pretty or interesting. But in the case of mathematical modeling, it's really about doing useful things. Number one, it represents reality and real situations. But the kicker here is they aren't real. The models aren't real. And it's worth noting that sometimes people get caught up and they make a mathematical model and somehow they think that that model like exists in the world. You know, F equals MA is a mathematical model. It doesn't actually exist in the world. You don't like walk outside, lift up a rock and find F equals MA written underneath it, right? But physicists use that model all the time because it works and it represents reality very, very well. And so the other thing that models let us do is that they let us examine and predict. And the prediction part is especially important. And we're able to do that based on quantities and qualities. And these two words are purposely similar but still different. Qualities means we're talking about measurements. Measurements, numbers, right? And then qualities is talking about relationships. So if you ask, what color an object is, you're getting a quality of that object. But if you ask what wavelength is the light emitted from an object, you're asking for quantity. Oh, I missed an N. Quantity. Right? So the other thing that models do is they let us know what's important, or let us see what's important and what's presumed. And this is another thing that we sometimes forget about models, that models really point out to us what's important about a particular situation because, hey, it's not behaving like what I see in the real world. I have to add this extra term in order to make it behave that way. That means there must be something going on there. And the other thing that it does is it allows us to examine our presumptions about the world, right? If you included a constant in this particular model to allow you to adjust, then there must be some reason to do that adjustment, right? If you added another term to your model, there must be a reason that you're doing it. But really, models also do two things. They are testable, and that's super important. And they're improvable. I think I spelled it right. Through iteration. In other words, we can test a model, but we can always make it better by doing practicing with it, by going run after run after run. And you're probably not at all shocked or surprised to figure out that there's some general steps for modeling, and these are going to make perfect sense when you see them. The first one is you're going to state your assumptions. So what do you assume about the situation? The second thing you're going to do is describe variables and constants. The third thing you're going to do is describe parameters. And we'll get into parameters here in a minute. Parameters. The fourth and kind of the last thing is really to create and generate. There we go. And then use the equations. Sometimes they may not be equations, but for the most part, these are where we're going to have our differential equations. Right? So we should be able to start with assumptions, and sometimes stating assumptions and describing variables. Sometimes that's done in words. Sometimes it's done in symbols. Sometimes it's just done with a diagram, right? So let me give you an example of a really super simple situation that we can try to model and understand mathematically. So the rate of change of a population with constant birth and death rates is, in simple cases, proportional to, there's that phrase, the size of the population at any time. So we've got some things that we're going to need to model here, some things that we need to make sense of. So the first thing, proportional to the size of the population, that means the rate of change of the population is proportional to the size of the population. That means, if you remember, A equals K times B. There's a constant of proportionality there. And in this case, our A, the first thing is the rate of change of population. It's presumed to be with respect to time. But if you think of this as the rate of change of population, and B is the second quantity, it's proportional to the size of the population at any given time. We need to come up with some way of describing that relationship, and we have an equation that's going to relate these two things. So we need to come up with a way of describing that, writing that in terms of math. And so what we might do is kind of borrow some shorthand for the rate of change of population and the size of the population. We'll use a simple variable, p of t, for our population variable. And so the size of the population at any given time is p of t, and that means the rate of change of population would be dp dt. Now notice I write dp dt, but I don't write dp of t dt, just because we don't need to, right? It's implied. So now down here, when I'm writing this in terms of math, I can say dp dt is equal to some constant times p. Now I can write p of t, but it's implied. And so what this is doing is it's telling me what my dependent variable is and what my independent variable is. And it's also telling me that I have a constant sitting in there. So in this particular situation, kind of spelling things out in detail, I can say that I'll even use units, or unit, I don't want to say unit analysis here, to try to make sense of what's going on here. Using a little bit of unit analysis, we can say that P is in population of individuals, is in units of individuals. And it could be individual people, it could be individual viruses, it could be individual whatever, doesn't matter. P is units of individuals, and the other variable, the independent variable t, is in units of time, whatever that happens to be, days, minutes, seconds, hours, whatever. And then of course there are two other things in this equation that we have to pay attention to. There's k, and then there's dp dt as a quantity. So what is dp dt? Well, it's a rate of change of population over a change in time. So this is literally in units